In this video and the next, we're going to develop from scratch algorithm for the all pairs shortest path problem, rather than by relying on the aforementioned reduction to the single source version of the problem. So in this video, we're going to develop the relevant optimal substructure lemma. In the next video, we'll culminate in the dynamic programming algorithm. It is a famous one, the Floyd-Warshall algorithm. Before developing the optimal substructure, let me just tell you a little bit about where we're going. The optimal substructure we're about to identify will lead to a dynamic programming solution via the usual recipe, which we've now seen over and over and over again. It's going to solve the all pairs shortest path problem in O of n cubed time, so we get a bound independent of the sparsity, n cubed even if the graph has negative edge lengths. This algorithm is known as the Floyd-Warshall algorithm. Last video, we discussed the performance that you get by just running a single source shortest path subroutine n times, and the Floyd-Warshall algorithm is a better solution in many situations. So first of all, for graphs that have general edge lengths, that is, edge lengths that are allowed to be negative, then Floyd-Warshall is looking pretty good. Remember, with the previous solution was to run the Bellman-Ford algorithm n times. We can't use Dijkstra's algorithm because that's not generally correct with negative edge costs. And if you run the Bellman-Ford algorithm n times, you get a running time of n squared m. So even in the best case for Bellman-Ford sparse graphs, we're doing just as well with Floyd-Warshall. We've got a cubic running time. And we're doing quite a bit better for dense graphs. There, n times Bellman-Ford would give us n to the fourth, a quartic running time, whereas here we're getting cubic. Now, for graphs with non-negative edge costs, reducing to the single source problem is actually a pretty good solution because Dijkstra is so fast. So if you run Dijkstra n times, your running time is going to be n times m times log n. So for sparse graphs, you'd really want to use Dijkstra n times rather than Floyd-Warshall because you get a running time roughly quadratic in n as opposed to the cubic running time we're going to get here. For dense graphs, it's not so clear. If you run Dijkstra n times, you're going to get a running time which is ballpark cubic, so that's going to be roughly the same as Floyd-Warshall, and you'd expect them to be comparable. It's not clear which one would do better in practice. If you had to choose between those two solutions for dense graphs, you'd really want to code them both up and pick whichever one seemed to do better in your domain. One place you see the Floyd-Warshall algorithm used quite a bit is for computing the transitive closure of a binary relation. And in graph theoretic language, you can think of the transitive closure problem as computing all pairs reachability. So that's a special case of all pairs shortest paths where you just want to know whether the shortest path distance is finite or infinite. For each pair of vertices, you want to know, does there exist a path from the one vertex to the other or not? And if all you care about is the transitive closure problem, if all you care about is one bit of information for each pair of nodes, connected or not, as opposed to more generally what the shortest path length is, then you can do some optimizations in the Floyd-Warshall algorithm to speed up the constant factors. But I'll leave it to you to read up on the web about that if you're interested. Now, I realize that this cubic running time is maybe not super impressive. In general, as we've been talking about dynamic programming algorithms, we've been starting to see for the first time in these courses a proliferation of algorithms which, while polynomial time, while way better than exponential time, you wouldn't really call blazingly fast. We've seen a lot of quadratic running times. Now we're seeing some cubic running times. So that's kind of a bummer, but I am still teaching you the state of the art. As we mentioned this on the last video, it remains an open question to this day whether there are significantly subcubic algorithms that solve the all pairs shortest paths problem. So now let's formalize the optimal substructure in all pairs shortest path, which is exploited by the Floyd-Warshall algorithm. A quick digression first, though. At the beginning of the class, I hope that, if I'd shown you this Floyd-Warshall algorithm, you would have said, wow, that's a really elegant algorithm. How could I have ever come up with this? Whereas now that you're approaching the black belt level in dynamic programming and you see just how mechanically the algorithm, this famous algorithm, is going to fall out of the really quite easy optimal substructure, I hope you say, how could I not have come up with this algorithm? Now, I don't mean to take any credit away from the solutions of Floyd and Warshall. There is one really great idea in how they phrase this optimal substructure. Remember, we talked about this before the Bellman-Ford algorithm. It can be tricky to apply dynamic programming to graph problems because there isn't really an ordering in the input. You just get this bag of vertices and this bag of edges, and it's often unclear how to define bigger and smaller subproblems. So the really nice solution in the Bellman-Ford algorithm was to introduce this extra parameter I. I was a budget on the number of edges, or roughly equivalently, the number of vertices that you were allowed to use in a path between the origin and destination for a given subproblem. This naturally induces an ordering on subproblems. The bigger the edge budget, the bigger the subproblem. We're going to do something similar, but even a little bit more stringent in the Floyd-Warshall solution. We're again going to restrict the number of vertices that can appear in the middle of a path between a given origin and destination in a subproblem. But more than just the number of the vertices we're allowed to use, we're going to restrict exactly which vertices, the identities of the vertices, that the algorithm is permitted to use to get from the given origin to the given destination. And in many ways, the restriction we're going to impose is totally analogous to, say, the knapsack problem, where there wasn't an intrinsic ordering on the items, but we imposed one anyways, and then we just look at prefixes of the items. And bigger subproblems were ones with bigger prefixes of items. Here, we're going to impose an arbitrary ordering on the vertices, and in a given subproblem, you're only allowed to use some prefix of the vertices as internal nodes in a path, and then, of course, the bigger the prefix you're permitted to use, the bigger the subproblem. So to be a little bit more formal about it, let's just impose some arbitrary ordering on the vertices capital V, name the vertices 1, 2, 3, all the way up to n. I don't care how. And I'm going to use the notation capital V superscript k to denote the prefix of the first k vertices, vertices 1 through k. So let me start now setting up the optimal substructure lemma. In contrast to the Bellman-Ford case, I'm only going to prove the optimal substructure lemma for input graphs that have no negative cycle. We'll address the case of negative cycles after we're done with the algorithm. Suppose for now there isn't one. So what then are the subproblems going to be? Well, it's going to be quite analogous to Bellman-Ford. In Bellman-Ford, we were solving the single source shortest path problem. So we needed to compute something for each destination. So that gave us a linear number of subproblems. And then for a given destination, we had this parameter I controlling the edge budget. So that was another linear factor. So we had a quadratic number of subproblems. Here it's going to be the same, except we also have to range over all origin. So we're going to get a cubic number of subproblems. Specifically, a choice for the origin, n choices. A choice for the destination, that's n more choices, plus which prefix of vertices we're allowed to use. So that's still another n choices, so cubic total. So now we focus on an optimal solution to this subproblem, by which I mean amongst all paths which begin at the vertex I, end at the vertex j, and strictly in between I and j as internal nodes contain only vertices from 1 through k. Amongst all of those paths, we look at the one with the shortest length. And because we're looking at the case of no negative cycles, we can assume that this path has no cycles. It's a cycle-free path. So rather than state the conclusion of the optimal substructure lemma right now, let me just make sure you understand what one of these subproblems is. So let's suppose that the origin is the vertex that we've labeled arbitrarily 17. The destination j is the vertex we've labeled 10. And let's suppose k at the moment is only 5. Consider the following graph. Imagine this is a little piece of some much bigger graph. Now, I hope it's clear what the shortest path is between 17 and 10. It's the bottom 2-hop path. That path has total length minus 20. On the other hand, for the subproblem we're dealing with, k equals 5. So what that means is we have this extra constraint on which vertices we can use in the middle of our paths. Now, to be clear, this constraint, k at most 5, that can't apply to the origin and the destination, right? I is 17, j is 10, both of those are bigger than 5, but we don't care. Obviously, any path from I to j has to include both the vertices I and j. So the constraint only applies to vertices in the middle of the path, but this bottom 2-hop path, unfortunately, makes use of the node 7. So that path does not obey the constraint. It is not at most 5. So that path is disallowed. We cannot use it. Therefore, the shortest path from 17 to 10 that makes use only of the first 5 labeled vertices as intermediate ones would be the top 3-hop path, which has the bigger length of 3. Okay, so I hope it's clear what a subproblem corresponds to. It corresponds to a choice of I, the origin. That's, again, just some vertex labeled something from 1 to n. Similarly, there's a choice of the destination, some other vertex j, which is labeled something from 1 to n. And then there's a choice of the bound k, which governs which vertices you're permitted to use internal to your paths. Again, the constraint doesn't apply to the endpoints, just the vertices in between the endpoints. And in the subproblem, the choice of k says you can only use vertices 1 through k internal to your paths. So hopefully that makes sense. Let's move on to the full statement of the optimal substructure lemma. All right, so this is actually going to be one of the simpler optimal substructure lemmas that we've seen in a while. We're back to the glory days of only two cases. The first is trivial. If the shortest path from I to j using only vertices 1 through k as intermediaries doesn't even bother to use the vertex k, well, then it better well be a shortest path from I to j that uses internal nodes only from 1 to k minus 1. Now, it's in case 2, it's going to become apparent what a great idea ordering the vertices, looking at prefixes the vertices, is when you're considering the all pairs version of the shortest path problem. Suppose this path P from I to j does indeed use the vertex k in the middle. Well, then we can think of the path P as comprising two subpaths. The first path P1, which starts at I and goes to the vertex k, and then a path P2, which starts at k and goes to the destination j. Now, here's what's cool. So on this path P, the internal nodes between I and j all lie in 1 through k. Moreover, this path P, remember, is cycle-free, so the vertex k appears exactly once, not more than once. So therefore, if we split the path P into these two parts, P1 and P2, internal to P1, strictly in between I and k, there's only vertices between 1 and k minus 1. Similarly, strictly between k and j and P2, there's only vertices between 1 through k minus 1. Thus, both of these paths P1 and P2 can be thought of as feasible solutions to smaller subproblems, subproblems with an even tighter budget of k minus 1 on the internal nodes that are allowed, and these aren't just feasible solutions for smaller subproblems, they're optimal solutions as well. So how slick is that? That the maximum indexed internal node just splits this shortest path into two shortest paths for smaller subproblems. And you know what? At this point, I am so confident in your facility with dynamic programming, I am not going to even bother to prove this statement. You are totally capable of proving this yourself. The argument is really quite similar to Bellman-Ford. I encourage you to do it as an exercise.